Hello to our friends joining us via recording. Today we are wrapping up lesson number 8 about the skeletal system. Remember that for the skeletal system, we are not only learning how it normally works, that's our job in class today, but we are also studying what happens when things go wrong. That's the skeletal system disorders assignment. Both of these assignments are due Sunday night at the end of spring break, so right back before we come back to class. I would recommend, though, trying to wrap up lesson number 8 earlier rather than later, just to make sure that you're not going crazy and trying to learn everything the night at the end of spring break. So that's my plug for working ahead a little bit per our assignment checklist. Just stay on track, get some stuff done. We should be in good shape. We wrapped up in class yesterday lesson number 7 about the integumentary system. And the last idea in lesson number 7 about the integumentary system is we were talking about the way that your body maintains its internal conditions. What did we say was our anatomy word for maintaining those conditions? Yeah, Kira mentioned it for us in the chat here. That word is called homeostasis. So the last thing that we talked about in lesson number 7 was the idea of homeostasis. This is the fact that even though outside changes, so again, in 3 weeks, it'll be super hot. Your inside temperature is still always going to be the same. Or even though maybe it's been 5 hours since you last ate food, your blood sugar level is going to stay the same. That's homeostasis, trying to maintain our internal conditions even if other stuff changes. So when we think about homeostasis in general, there's this normal condition that we like to be at. What do we call normal? Or what is it that your cells typically maintain? Yeah, exactly. That's a thing called the set point. The set point. Now, here's a reminder, though, with this set point word. Remember that it's not just one value. It's not just one number. So we talked about thermoregulation. We talked about body temperature. Remember that we said that 98.6 is what we usually talk about as the set point for body temperature. But really your body's happy kind of anywhere in the range of 97 to 99-ish. That's within normal range for you. That's why a lot of times when they talk about, well, do you have a fever over 100 degrees? Or over 99.8. They're adjusting for the fact that it's not just one point. It's not just 98.6 that's normal. There's a range of normal within that. So the set point of a homeostasis loop is all the possible normal values for your body, the normal conditions. If something isn't normal, we would detect that. So remember, in the case of temperature, we were talking about how you have receptors in your skin and you have receptors in your brain that are always checking your temperature to see what your body temperature is at. They're collecting information. That information either says we're hot, or that information says we're cold, or it says we're normal. It could be any of those. They collect that information and they send it somewhere to a part of the loop that can process that information, the part that can figure out how we get back to normal. Yeah, exactly. When we talk about this part of a homeostasis loop, that's called the control center. So the control center is the place where we send information to do processing. Hey, I'll give us a word that's going to come up in the nervous system. The word that we're going to be using a lot when we start talking about the nervous system in lecture, we call it integration. So we integrate the information, meaning we take all of the readings from our receptors. They all say it's cold, so we collect all of that information and we figure out that what we need to do is we need to warm the body back up. So the control center figures out what all those messages mean. Oh, everywhere is reading that we're cold. We need to fix that. And the control center then can predict what we would do to fix that. The control center is going to send that message to the things in the body that actually help us get back to normal. What are those things that get us back to normal? What are those called? Yeah, exactly. So the part of a homeostasis loop that actually gets us back to normal are the things called the effectors. Your control center is awesome at figuring out what should happen, but your control center doesn't actually have the ability to change anything. What actually changes things are the effectors. Those are what gets us back to normal. Those are what have an effect. Absolutely, like Audrey said, it has an effect on us. So when you're thinking about and you're doing those homework assignments and it's talking about changing things or making stuff happen, that's the job of the effectors. When we're using words like predicting the right answer or the right response, when we're using words like integrating sensory information or processing information, that's the job of the control center. So all of these or statements that we see here, remember they reference back to our picture that shows a general homeostasis arc. So make sure we're familiar with what each of these points on that arc are about. I guess the other thing that we had on there that didn't make it onto my list here were those receptors. So one other word in the homeostasis arc, those receptors that collect the information. So the receptors are listening. Typically what they hear is that we're right around the set point, but if we hear anything that's not right around the set point, the receptors send that information to the control center. The control center figures out how we need to respond and activates the effectors to make it happen. So typical homeostasis loop, big picture. Compare that to a more specific example of how homeostasis works. Remember that yesterday we talked about the specific kind of homeostasis called thermoregulation. Thermoregulation. This is your body's ability to maintain your normal temperature even when it's hot outside, or recently when it was cold, outside and inside. Thermoregulation kept us right around normal, close to our set point. Now it's possible for your body to get too cold or too hot. When I am talking about the state called hypothermia, am I too cold or too hot? Hypothermia. Yeah, so hypothermia, hypo, remember when we talked about concentrations, meant low. Or when we talked about the hypodermis, that was the part of the skin underneath the dermis. Hypothermia is when our body's too cold. What do I call it when my body's too hot? What if we've got the opposite extreme? My body is too hot. Yeah, now we flip over, right? Now instead of being hypothermia, now it's hyperthermia. Hyperthermia. So these are the two conditions when we are not at homeostasis, because either we're too cold or we're too hot. Either of those, we've moved away from our set point and we want to try to get back. We see in our first prediction statement here this word vasodilation. Remember that vaso meant blood vessels. And when we use the word dilation, it means that we're making them wider. Yeah, they're more open. I like that. Would we want our blood vessels, especially the blood vessels in our skin, to be wider when we have hypothermia or hyperthermia? When do we make those blood vessels wider? Yeah, exactly. We are going to make those blood vessels wider when we have hyperthermia. Hyperthermia, meaning we're too hot. Remember that your blood is one of the places in your body where we store a lot of heat. So if we have too much heat in the body, we're going to send some of that heat out to the skin using the process of vasodilation. So your heat would radiate off. This is why your skin gets really hot after you exercise, or why you might look a little more flushed after you exercise, because your body is literally sending extra blood to the skin to try to get rid of that heat. When I use this word vasoconstriction, what's happening to my blood vessels when we do vasoconstriction? This is kind of my opposite word, right? Vasoconstriction. Yeah, now my blood vessels, so constriction, we're getting smaller, or we're closing. Absolutely, they're squeezing in on themselves. Hey, let's see if we can make a lab connection here. Vasoconstriction is done by the kind of muscle that's found inside blood vessels. Do we remember which kind was inside blood vessels? Yeah, a couple of us are voting correctly. Smooth muscle was the kind of muscle that you find inside blood vessels. So whether we're talking about vasodilation or vasoconstriction, both of these processes are done by smooth muscle. Hey, we're going to talk all about muscles in lab this week, but here's a reminder for us. When we talk about smooth muscle, remind me, you do or do not decide when smooth muscle contracts. Are you in control of smooth muscle? Yeah, we are not in control of smooth muscle. That's absolutely right. It's what we call involuntary. So you're not deciding whether your blood vessels are really big or really small, which means that you really don't have a lot of control over whether or not your skin is losing a lot of heat or trying to save heat. But I think we talked about this before. Remember that it's good that you don't have to control smooth muscle, because smooth muscle is also found all through the digestive system. And if you have to think about making sure that your intestines contract, that would literally be all you would do all day, every day. So we are grateful that we don't have to control smooth muscle. That helps us not only with thermoregulation, with working on our temperature, but also with digestion. Yeah, Kira says that'd be the only thing that we'd think about all day. Very, very true. All right, so when your body decided to make your blood vessels smaller, did that mean you have hypothermia or hyperthermia? If we decided we need to make those blood vessels smaller. Yeah, exactly. That would be an example of hypothermia. Hypothermia. By squeezing those blood vessels smaller, we're not going to lose as much heat outside the body. Hypothermia. When we talk about activating your skeletal muscles, so them acting as one of our effectors, when do we activate those skeletal muscles? Hypo or hyperthermia? Who does skeletal muscles? Yeah, exactly. Hypothermia. When you are too cold, your body will activate your skeletal muscles to make you start shivering. So shivering is a effect that we see from hypothermia. Yeah, Kira said she has a question. What's your question? So Kira's question is, would we also say that smooth muscle is an effector because we do vasoconstriction? Yes, that would be correct. The thing to keep in mind with that, though, is it's a little bit tricky when we're talking about what smooth muscle is an effector for, because technically both of my conditions, whether I'm too hot or too cold, I will always change the smooth muscle. So typically if we're thinking about the kinds of muscle that respond when we're having hypothermia, yes, it would be correct that we contract our smooth muscles and that we contract our skeletal muscles. When we have hyperthermia, we don't do anything with those skeletal muscles, but we technically send an inhibitory message. So we send a message to the smooth muscle and we tell them not to contract. So smooth muscle, we could actually say, is actually involved in both of these conditions. It's an effector whether we're too hot or too cold. What that effector does is different depending on what state we're in. So we could definitely say, we could add to our list here, I'll put a note underneath it, skeletal muscle and smooth muscle. They are both effectors that we see activated when we have hypothermia. When we have hypothermia, we contract the smooth muscles. When we have hyperthermia, we relax them. We still send them a message. They still do something. What they do is they relax, but they're still doing something. So my last statement, I'll fill it in for us. If you hadn't already guessed, the last statement, when we use those endocrine glands, is when we have hyperthermia, when we're too hot. Endocrine glands, again, what did those ones make? What do endocrine glands secrete? Hopefully we know this from lab. Yeah, exactly. It's that watery sweat. And actually, if you remember from the lab packet, it even called it thermoregulatory sweat. Thermoregulatory sweat. So endocrine glands make that watery sweat that cools you off. We could also say, like our statement above, endocrine glands are an effector. We could also say smooth muscle. In this case, when we talk about smooth muscle being an effector for hyperthermia, we're sending the message to relax. So we're telling them to stop contracting. We just rediscussed the process of thermoregulation. We also talked about homeostasis loops overall. Do we have any last minute questions about those two things? Can I get some emojis? Last semester, I used to start with emojis, and I just get so excited about our virtual classrooms this semester that I forget to ask you all for an emoji. So I'm loving it, getting some emojis here. Awesome. I will give you your daily penguin from me. Oh, nice. Audrey sent me an alien. Let's see what other fun things I can find. I will also send you, here we go. I'm also sending you a fox because my 8-month-old's nursery, actually he's 9-month-old now. I gotta get with the program, man. My 9-month-old's nursery is decorated like a fox. So that was our theme for him. All right. Well, please plan to try to wrap up the lesson number 7 homework assignment. If you haven't already for the integument for lecture, try to get that wrapped up today, just so that you're done with the skin stuff and you can really focus on the skeletal system stuff. That's where we're going to head today. And remember that on Friday, we are having our review session to review anything from unit number 2. So start compiling a list right now. I will ask you tomorrow at the end of the class if you can let me know some of the things you want to talk about. That is Friday. We will hit on anything that you would like from unit number 2. I believe during yesterday's class, this is where we wrapped up. Is that correct? Was this the last thing we talked about yesterday? Yeah, Caitlin asked in the chat, how are we finishing unit number 2? I know, it's like flying. Don't worry, unit number 3 is going to go much more slowly. We only have 3 things to talk about, but we are talking about them in depth. Okay, perfect. So sounds like this is the last thing or one of the last things that we talked about. I just want to remind us before we dive a little bit more deeply into how our bones form. Remember that there are 2 kinds of bone tissue. There's compact bone tissue that's typically seen on the outside of a bone, and then there's the spongy bone tissue that we find a little bit lining the medullary cavity, and we also find a lot in those 2 epiphyses, in the ends of a bone. Hey, here's a wink, wink, nudge, nudge, by the way. You will notice on the homework assignment and on the Unit 2 exam that I'm going to use those lab words, epiphysis, diaphysis, referring to the parts of the bone. So if you were a little bit dicey on those things, make sure we go back and review them. Remind me, this part here in the middle, is this the epiphysis or the diaphysis, this long middle part? Wow, look at us typing the whole word. You all are awesome. I totally just expected a bunch of D's. You're great. So this middle part here is absolutely called the diaphysis. That's the shaft of the bone. And then we have the 2 epiphyses, the 2 ends of the bone. That epiphysis word is really important when we start talking about the way that our bones form. I'm going to come back to this picture in a moment. I want to highlight that there's these things called the epiphyseal plates. The epiphyseal plates, meaning they're a dividing line between the epiphysis and the diaphysis. So this word epiphyseal plate, it looks like the word epiphysis, and that's on purpose, because that's where I find it, by the epiphysis, by the ends of the bones. So we're going to talk about now how we build our bones. Remind me, before we get started, we're talking about building bone tissue. What specific kind of tissue do your bones start as? Before it's bone, the skeleton is, yeah, exactly, it's cartilage, and in particular, it is hyaline cartilage. Hyaline cartilage, absolutely. Remember, the fetal skeleton is made out of hyaline cartilage. Yeah, Audrey's mentioning in the chat, remember that hyaline cartilage looks like we've got those deer tracks in the snow. That's a particularly good reminder because one of your learning objectives for this lesson is you do need to be able to identify these kinds of tissues. So this should be super easy since we've taken the midterm exam. We need to know what hyaline cartilage looks like. We need to know what spongy bone looks like. We need to know what compact bone looks like. That's a learning objective we can check off right now, right? Because we already did that for the lab exam. So hyaline cartilage is what the fetal skeleton starts as. That's what it looks like. Can you all, does anyone remember? I told you there was a beginning that whenever you see it, always means cartilage. When I talk about the extracellular matrix or the cells, yeah, anytime I see cartilage or anytime I see the beginning part chondro always means cartilage. Yeah, so absolutely, Rima's mentioning those things called chondrocytes. Those are my cells in cartilage. We also had that stuff called chondroitin sulfate. I won't make you spell that one. That was our extracellular matrix in cartilage. So anytime you see chondro, anytime we see chondro, we are thinking cartilage. Chondrocytes, chondroitin sulfate, it's all about cartilage. So this process that we're talking about with the way that you build bones, the way that we build bones is called endochondral ossification. Endochondral ossification. So we're going to split up this long word into a bunch of different parts. Let's start with the last part. When we see ossification, it's got that beginning part os in it. Os means bones. So ossification is the process of building bones, bone building. Let's go to our big word here. We've got chondral in here. Remind me again what chondro always means. Always related to, yep, always related to cartilage, absolutely. And when we use this part endo, endo means inside. Endo is inside. So literally, when I use this phrase, endochondral ossification, what it literally means is inside cartilage, bone building. When we're building your bones, I know endochondral ossification sounds way scarier than inside cartilage, bone building. We got that. We can do that. So endochondral ossification is the way that I take the fetal skeleton that's made out of hyaline cartilage and I turn it into bone tissue. Now, I saw out of the corner of my eye earlier in the chat, someone had mentioned that there are some bones in the body that don't form this way. That is correct. Mentioned that the flat bones are bones that don't form this way. Can we think of some of the flat bones in the body, by the way? Yeah, so Kaylin mentioned the ribs. Let's make ourselves a little list of some of the flat bones that don't use this. Yep, so we've got the ribs, we mentioned the sternum, mentioned a lot of the skull bones, yep. Did I get them all? Yeah, and then there's a couple in the pelvis as well. Yeah, perfect. So when you think about flat bones do not use endochondral ossification. The name of the process that they use that we're not going to go into in our class, so you're not responsible for this process, but the process they use is called intramembranous ossification. Intramembranous ossification. Not a trick question. What do you think these bones start as? They're not starting as cartilage. We don't have chondro. Yeah, they start out as a membrane. So they actually start off as a really collagen-rich membrane, just a flat sheet with lots of fibers in it. They'll turn into bone in a different way than those hyaline cartilage models will turn into bone. So we're not going to focus on this. I think at least one of the videos I have you watch, it goes through and shows you this process. It's not as scary as it sounds. You just basically send some bone cells into the membrane and they turn it into bone tissue. But I'm not going to ask you to know anything about this one. That's the other way that a few of the bones in my body, those flat bones, are made. Most of the bones in your body do this. Endochondral ossification. Inside cartilage bone building. So let's talk about how this process of inside cartilage bone building works. Step one, if we're going to build a bone inside cartilage, I need to have cartilage. So very early in embryonic development, very early on, we develop this cartilage model of each of the bones in your body. That cartilage model throughout the developmental process in utero is going to continue to grow and expand over time. But around 9 weeks, we get to a size where that cartilage model is big enough that your body starts to decide, hey, I think I'm going to turn into a bone one day. I'm growing up and I want to be a bone. So my chondrocytes, my cartilage cells that live kind of toward the outside of this model, they get really excited because they found their purpose in life. They're gonna build bone. They decide to start grabbing calcium and working with the nearby blood vessels to build something called the bone collar. So the bone collar is a really thin layer of bone tissue on the outside of the cartilage model. We're starting to develop bony tissue. Now, this is all well and good because we're going to turn into a bone. But the problem is bone connective tissue with its calcium phosphate, bone connective tissue with calcium phosphate in it is really strong, really resistant to damage, also really good at blocking nutrients and oxygen from getting into the cartilage. So remember when we talked about cartilage, that cartilage had this stuff here called chondroitin sulfate, and that was squishier, and that was a lot better at sharing nutrients and oxygen. When we start putting that calcium phosphate on the outside of the bone model, these chondrocytes in the middle of the cartilage, they start to die because they don't have oxygen or nutrients anymore. So the very middle of the hyaline cartilage becomes calcified, meaning those bone cells are dying. They think about them kind of sending out an SOS message like, help us, we're not getting oxygen or nutrients anymore. But that message isn't received, or it's not received early enough. By the time we send in a nutrient artery, which just like its name implies, this is how nutrients get to my cells. By the time that nutrient artery gets inside, all those chondrocytes have completely died. So we bring in oxygen and nutrients. The chondrocytes are dead though. What also comes in with this nutrient artery are a type of cells called osteoblasts. Osteoblasts. We're going to talk more about them here in a bit. Anytime you see blast, we're thinking builder. So nutrient artery comes in, brings with it nutrients, brings with it oxygen, and brings with it the kind of cells that can build bone tissue. So when those osteoblasts get in here, they develop what we call the primary ossification center. The primary ossification center. Hey, underline, highlight, star idea with the primary ossification center. We find it in the diaphysis. We find it in the shaft of the bone. Before we make this primary ossification center, we build our bone collar on the outside. That kills my cartilage in the middle. When I bring in my nutrient artery, I build the primary ossification center in the diaphysis of the bone. We build bone here. The process of fetal development continues. So we start here in the middle of the diaphysis, and we expand and expand this space with those osteoblasts until we fill this whole diaphysis with bone tissue here in the middle because of those nutrient arteries and veins. As the bone continues to grow though, remember that we still have the epiphyses, the ends, that are made out of cartilage tissue. Because my blood vessels came into the diaphysis, not into the epiphyses. So I need to deal with this. Dealing with that is how we form the secondary ossification centers. So shortly after birth, or right around the time of birth, blood vessels also enter the epiphyses of the bone. They enter the ends of the bone. Again, when those blood vessels come in, they're bringing with them osteoblasts. So they build all the bone tissue that we find in the epiphyses of the bones. So epiphyses, the ends of the bones, that's where I find the secondary ossification centers. The diaphysis of the bone, the shaft of the bone, is where I find the primary ossification center. Throughout childhood, throughout adolescence, you will continue to increase the amount of bone tissue that's being formed in your bone, but we will always keep some hyaline cartilage in a few places. One of them that we're about to really focus on is called the epiphyseal plate or the growth plate. This is some cartilage that we keep around as long as you're growing. It's going to help us keep making the bone longer. At the very ends of these bones, though, you can also see what they're calling articular cartilage. Articular cartilage helps to form articulations or joints. This kind of cartilage is always around, so this is never going to go away. The epiphyseal plate will go away when you're done growing. The articular cartilage is there forever. Yeah, it helps, like Fanchen mentioned, to provide that smooth surface for movement. This is why, too, if someone's having some issues with their joints, if the joints are grinding a little bit, that could be because some of this cartilage got worn away. So articular cartilage is normally there your entire life, and it's there to make that smooth surface for articulations or for joints. That epiphyseal plate is the way that your bones grow longer, as we're going to talk about here in just a moment. Before I move on, what questions do we have about endochondral ossification? Endochondral ossification. Do I have any thumbs ups? We go nice and silent. Okay. Several thumbs up and a bone. I like it. I will take it. Okay. Well, let's focus then on this part, the epiphyseal plate, some of our cartilage that doesn't go away right away when we're doing endochondral ossification. So the epiphyseal plate is a structure that you can actually see in all of the long bones in your body. Let's see if we remember this, because this was a lab thing. If a bone is a long bone, what does that mean? How do you describe that shape? If a bone is a long bone. Yeah, exactly. It's just like its name says, right? It's longer than it is wide. Absolutely. So these are bones like the humerus in your arm, the femur in your leg, but it's also bones like your phalanges. This one to me looks a lot like a phalanx, like a finger bone. So inside your phalanges, when you're still growing, you actually have these growth plates or these epiphyseal plates in there as well. So the goal of epiphyseal plates are to help your bones grow longer. We're going to use the fact that cartilage can divide more easily than bone cells can. We're going to use that to our advantage. So we've got this layer of hyaline cartilage called the epiphyseal plate. At the top, just above the epiphyseal plate, so kind of right here, up here we have what's called the resting zone. So we can see our resting zone where there's some cartilage here and then a little bit of bone tissue up above it. The job of the resting zone at the very beginning of the epiphyseal plate, it's just an attachment point between the spongy bone and the epiphyseal plate. So chondrocytes that live in the resting zone of the growth plate, they're not really doing anything. They're resting and they're attaching things. We move into probably the most important zone of the growth plate called the proliferation zone. The proliferation zone is where our cells are doing mitosis. There's a lab word, mitosis. What's happening in mitosis? What was the easy way to describe mitosis? Yeah, exactly. It's all about division, right? So when we look at the growth plate, the way we actually grow or make new cells is in this part here called the proliferation zone. The way that you recognize the proliferation zone, a lot of people describe it looking like a stack of coins on top of each other. When our chondrocytes do mitosis and cytokinesis super quickly, they don't actually have time to push each other away. Like they just divided and then they divide again and again, and we end up with these big long lines of cells that just keep dividing. That's what's happening in the proliferation zone. We're proliferating, we're dividing. We reach a certain point and we're far enough away from the resting zone and we've divided a whole bunch of times. Now it's time for us to get larger. Remember that hyper always means more or extra. Trophic has to do with the size of something. So the hypertrophic zone is the space where those chondrocytes, those cartilage cells, start to get bigger. So we see the hypertrophic zone in here where those chondrocytes are bigger. Notice that these chondrocytes for the most part are still pink. These chondrocytes for the most part here in the hypertrophic zone, they're still alive. They've grown really big, but they're still alive. Because once we get to this calcification zone, now the cells have started to die because the matrix around them is being calcified. In other words, we're going from chondroitin sulfate, the squishy stuff, to calcium phosphate, the hard stuff. When we go to that hard stuff, the cells start to die, and now we've got this kind of in-between tissue. It's not quite bone, it's not quite cartilage, it's this in-between stuff. That's why we transition into what we call the ossification zone. So the ossification zone is where we use our bone cells to take that weird nebulous tissue from the calcification zone and actually turn it into bone tissue. So there's no more chondrocytes left in the ossification zone, just bone tissue that we're building and building to make your bone longer. Just like in the epidermis, remember how in the epidermis we had all those layers, all the strata, where one layer grew and pushed the other cells up farther away? That's the same way that epiphyseal plate works as well. So cells that live here in the proliferation zone, they grow and push and push and push, which pushes cells into the hypertrophic zone. And as these get bigger, they push cells into the calcification zone, which ultimately pushes them all the way down here to the ossification zone. So the way we make our bones longer is by pushing down on the cells and the tissue from top to bottom to separate our parts of the bone tissue from each other. Epiphyseal plates, because they're made out of cartilage, are going to look different on an X-ray than bone tissue does. So when we look at an X-ray, we can actually see whether or not you have a growth plate. Notice how over here, hey, let's see if we can figure it out. This is, we're looking at one of our joints. We're actually looking at the knee joint. I'll help us out with that. If this is the knee joint, what bones do we see? Have any idea who these bones are if this is the knee? Yeah, so my big one going into the knee joint, the biggest bone in the body, is the femur up here. And then down below it, we can see kind of our T-shaped bone here, the tibia. And then we've got that little white lie, the fibula, next door. Somebody mentioned the patella. We would normally see that in the knee. I think that's this hazy part that I see back here. I suspect that this is a picture of the knee joint from the back so that we can see the femur really well, see the tibia and the fibula really well. Here, I'm going to really make you try to remember. When we're looking at your lower leg, which of these bones, the tibia or the fibula, which one is medial on the leg? Is the tibia or the fibula medial? Yeah, look at you all. Tibia is the medial bone. Fibula is the lateral bone. The way that I want you to help remind yourself of this, literally those two bumps in your ankle. Like, I want you to literally feel them, because that bump that makes up the medial side of your ankle, that's something called the medial malleolus. There's a bone marking word from the first half of lab, right? A malleolus. That's the bump in the medial side of your ankle. And then if you feel the bump on the lateral side of your ankle, that's called the lateral malleolus on the fibula. So those two bumps that you feel down there, the middle one is your tibia. The outer one is the fibula. Tibia and fibula. So this person, we looked at their leg. We're seeing their femur. We're seeing their tibia. We're seeing their fibula. Notice how when I do an x-ray, it looks like these bones are floating. It looks like they're not connected. I can see that in all three of these bones here, because all three of these bones here are long bones. I can see their growth plates. Compare this x-ray to this one over here. When I look over here, you definitely don't see floating bones. If you squint and try really hard, you can kind of see a little bit of a line. If you squint closely, you can kind of see a little bit of a white line right here where that growth plate used to be, or maybe a little bit of a line right here where the growth plate used to be. See, once we are done growing, typically about ages 18 to 21 is about when this happens, our epiphyseal plate turns into the epiphyseal line. Epiphyseal line. So we go from having a growth plate into a line of bone tissue. All of those chondrocytes become ossified. They all turn into bone tissue. So for me, if I were to look at my x-ray, absolutely 100%, I'm going to have an epiphyseal line. I am beyond the age of 21, alas. I am not as young as I used to be. For some of you, if we did an x-ray of you, you might still have your growth plate. You might still have some of that cartilage there. That's going to be important for you, both from your own personal health perspective, but also as someone in the medical field, because if you see a patient who has this epiphyseal plate, what can we tell about them? If somebody still has an epiphyseal plate, they've still got this cartilage here, what does that help us know? Yeah, it means that they are still growing. They still have the potential to get taller. Absolutely. The other thing that's interesting for us too about this, it is actually possible for you to break a bone right along this growth plate. So you can actually detach the two parts of the bone from each other where the cartilage tissue is. Sometimes when your bone is healing, it will turn the epiphyseal plate into an epiphyseal line. Remind me, what kind of tissue is an epiphyseal line made out of? What kind of tissue is that one? Yeah, this is bone tissue. Absolutely. Yeah, so bone tissue, we don't grow any longer. Cartilage tissue, we do. So if we break a bone and it causes that growth plate to become bone prematurely, it's done growing. It won't grow any longer. Yeah, so Audrey is mentioning her daughter did this a couple of different times. Yeah, and I had one student that one semester came up to me after class and said, yeah, my right arm is actually longer than my left arm because this happened to me. So if we have a break along this epiphyseal plate and it heals up as an epiphyseal line, we won't grow anymore. So it's important for us to keep that epiphyseal plate intact to allow our bones to keep growing until all on their own they decide that they're done growing. Yeah, so Kira's mentioning her experience as well, that they were working on one of the ligaments in her knee, and they had to wait for to do that procedure until she had her epiphyseal line. Yeah, absolutely. It's very important that we leave those growth plates alone until they're good and ready. So the growth plate turns into the growth line. Again, it's typically age range of like 18 to 21. It's pretty safe to say for most of your body, all of those growth plates are going to be gone. I think, yeah, I don't have the text. Do you have in your notes, there should be a question about this one, right? Did I give you a question about this X-ray in your lecture outline? Okay, perfect. Yeah, I don't know why I didn't copy my text into here. I am promising you. So here's something that we need to pay attention to. Dr. Ollis is promising that on the exam, unit number 2 exam, I am going to give you an X-ray like this. So here's a knee X-ray. I could give you an arm X-ray. I could give you a leg X-ray. I promise you on the exam, I'm going to give you an X-ray and I'm going to ask you what kinds of things we can tell about our patient based on the X-ray. So in this particular X-ray, see how, again, we can see these floating bones. So we can see spaces between the bone tissue. That tells us we still have an epiphyseal plate. If we still have an epiphyseal plate, remind me, we are or are not done growing. If I have an epiphyseal plate, I am or am not done growing. Yeah, I am not done growing if I have an epiphyseal plate. So if this is the X-ray that you have on the exam, first thing we could say about this student or this patient is that they are not done growing. They still have a growth plate, and because they have a growth plate, they're going to keep getting taller. So the next thing we could say, though, is because this person has a growth plate, we could take a guess on their age. I can't remember if you have some options in your notes about this. Is there an option for you? Don't think so? Okay, yeah, so Fanchin gets what I'm getting at, though. Whenever we see a growth plate in a person, that typically means that they are 21 or younger. And if I'm going to ask you to predict ages, I'm not going to be mean. I'm not going to give you like, this person is age 19, because at age 19, you might have a line or you might have a plate. I promise I'm going to be more straightforward than that. So with an X-ray like this, I might ask you, is this patient more likely to be 10 or 27? What would we say for this patient? Are they more likely to be 10 or 27? Yeah, exactly. Since we still have a growth plate, that means that we are under the age where the growth plate closes. Growth plate closes somewhere around 18 to 21. We're definitely more likely to be around age 10, for example. Here's what I would recommend for studying for this question on the exam. Remember how I showed you for lab Google Images, where you go over to Google, you type in something like growth plate or epiphyseal plate X-ray. Once you do your search, click over to images, and it'll pop up a page of a ton of different X-rays. The best ones are going to have pictures of a growth plate and a picture of an epiphyseal line right next to it. Or you'll at least get a ton of pictures that show you these floating bones. We want to get good at recognizing this epiphyseal plate on an X-ray. You've already studied what the bones look like because we learned that for lab, the names of all those bones. And we're going to keep learning the names of bones. Yeah, so Audrey's asking, what should we Google? You should Google epiphyseal plate X-ray. This is what you should put in Google when you're doing your Google search. epiphyseal plate x-ray and turn it into a Google Images search. And you'll get all kinds of pictures that'll help you get used to seeing what it looks like when we've got these floating bones. So we're going to want to check out, this is the knee joint. We're going to want to check out the shoulder joint, the wrist joint, the ankle joint. Most of the pictures you're going to see when you look this up are going to be of joints like that. So just get used to seeing what it looks like when those bones are floating. As long as you can recognize that, I think you'll do just fine on that question. But I wanted to give you a heads up. You know how Dr. Ollis is. I make you apply stuff, not just know it. So I'm going to make you apply what we're learning about these plates to those x-rays. Yep, I'm going to be sneaky, like Kaylin said, but you were warned that I'm going to be sneaky. Now we know what to expect, right? How do we feel about growth plates, growth lines? Thumbs up, thumbs down, something in between. Yeah, go for it, Fanchen.
Okay, just so I don't know if we're necessarily focusing on this, but I kind of wanted to know. So whenever we're going through mitosis and then the cells are going through the process, is that going kind of down towards or up in some bones, which depending on where it is, would it be going in the direction of the diaphysis?
Okay, yeah, and I apologize. I think I had seen that question and I forgot to answer it. Yeah, so when we talk about the growing, we are growing, we end up actually pushing the two epiphyses away from the diaphysis. I believe, I would need to look at this more closely to tell you for sure which orientation we do the actual growing in. I want to say that the resting zone is closer to the epiphysis, and then the ossification zone is closer to the diaphysis. But when we talk about them growing, just consider the fact that we're pushing down on, essentially, you're kind of, think of it like if you're on a trampoline. The epiphysis is on the trampoline that is the diaphysis, and it kind of grows upward. It's being pushed away to make it longer. So these two epiphyseal plates are growing in opposite directions. Again, I think the ossification zone on both of them is toward the diaphysis, and then the resting zone would be right next to the epiphysis, I believe.
Oh.
Does that help answer your question, Fanchen? I apologize. I should have caught that earlier. Perfect. All right. Well, we've talked a bunch about how our bones grow longer. We've talked about the role of cartilage in our bones. Let's talk now then about the specific kind of cells that we find inside bone tissue. So inside the bone tissue of the skeletal system, we have already talked about these ones. And I apologize, my formatting got all funky. So over here on the right, we have those cells called osteocytes. Hey, let's do a little bit of review. First question about osteocytes. Do I find osteocytes in compact bone or spongy bone? Where do osteocytes live? Compact bone or spongy bone? Yeah, look at you all. You're like, Dr. Ollis, you're being tricky again. Yeah, I can't fool you anymore. I can't pull a fast one on you. So osteocytes found in compact and spongy bone. They're found in both. And actually, to be fair, that is a statement that's true for all three of these types of bone cells. But in particular, I am asking you, one of your learning objectives is to compare compact bone and spongy bone. So we mostly focused on osteocytes as the cells that I find in compact bone and spongy bone. Remind me, with these osteocytes, we have a special name for their home. What do we call the home of these osteocytes? Exactly. Yeah, my osteocytes, they live in lacuna. That's their little homes. So when we're looking especially at compact bone tissue, remember that those lacuna are the dark black spots that you see. Inside of them are those osteocytes, the bone cells that live inside there. When you think about osteocytes, I want you to consider osteocytes to be the retired bone cells. Retired bone cells, as in kind of like retired people, or let's be real, all of us right now with COVID, you kind of just stay at home and don't really do as much as you used to. We maybe don't build as many things or break as many things. We're just kind of stuck at home, keeping our house. For me, I was going to say like keeping our house running smoothly, and then I was like, that's not true. For me, it's just keeping my house from burning on fire. Let's be real. I got those two littles at home. So just like osteocytes that are retired, they're just keeping their little lacuna, keeping to themselves, staying in the lacuna, making sure it doesn't go up in flames. When we talk about these cells, osteoblasts, these cells are much more active than osteocytes. I already said this earlier in class. Osteoblasts. This word blast, what did that mean? Yeah, it means builder, absolutely. And I just realized that I put osteoblast twice on this slide. My apologies here. Let's try this again. This middle one should say osteoclast. That's what your notes say. Osteoblast over here on the left, you guys are all totally right that blast means builder. Osteoblasts, these are my bone builders. Osteoblasts, if we're thinking about the bone cell circle of life, everybody starts as an osteoblast. Osteoblasts are going to spit out collagen proteins. Make sure I spell that right. Collagen proteins. And they're also going to spit out what are called calcium binding proteins. So calcium binding proteins, like their name suggests, bind to calcium. Collagen proteins are the proteins, remember from yesterday, that we said are kind of like the rebar. We spit these out to lay a framework for bone tissue, and then we spit these ones out to bring over that calcium phosphate. So osteoblasts are constantly spitting out these proteins that cause our bones to be built or to build them stronger. When an osteoblast has spit out so many collagen proteins and so many calcium binding proteins that it's completely surrounded by calcium phosphate, at that point it can't build anything else, and at that point it retires. So osteoblasts are super excited, they're super active, they help us to build great bone tissue, and when they're completely surrounded by bone tissue, they turn into osteocytes, the retired version of a bone cell that just stays home and makes sure that the bone tissue is functional. A completely different kind of cell that we have in our bone tissue is called osteoclasts. Whenever we see that ending part, clast, that's going to mean breaker. So osteoclasts are bone breaking cells. And these cells, I say they're completely different because these cells actually don't start as bone cells. They actually start as kind of like immune system cells. So they're formed in the bone marrow. They come out and we're building bone tissue. And they say, hey, this bone tissue looks a little bit weak. Let's break it down so that we can build it again. Or they'll say, you know, the way that we're walking right now, I need less strength in this part of the bone. Let's break this down so that calcium is available to build somewhere else. Osteoclasts spit out enzymes that break down bone. Enzymes that break down bone. Their job is to help with a process called bone remodeling. Bone remodeling, when we remake bone. So osteoclasts do the part of bone remodeling called resorption. Resorption, where they break down or they reabsorb the bone tissue that is there, putting that calcium back into the bloodstream, or making those amino acids and collagen available so that osteoblasts can go through and build bone tissue again. So when we talk about remodeling, which we'll talk about in terms of braces, for example, or when we exercise, remember that it takes two kinds of cells to do that. My osteoclasts that break down old bone tissue, and my osteoblasts that build new bone tissue. And remember, when an osteoblast does a really good job and it builds all kinds of bone tissue, suddenly it has no more space around it and it turns into an osteocyte. How do we feel about our three main types of bone cells? Osteoblasts, osteoclasts, osteocytes. Perfect. Okay, so here's what we need to keep in mind then as we're thinking about real life for you day to day. The activity of osteoblasts compared to osteoclasts, the rate that they work at is different depending on where you are in your life. So let's start with our picture here at the bottom. In our picture here at the bottom, we're starting with a child who's smaller, going all the way up to a child who's taller. When you're going through the process of growing taller, how do we think the rate of osteoblasts versus osteoclasts, who do we think is more active when you're growing taller? Yeah, so Kira's voting correctly that osteoblasts are more active when you're growing. Osteoblasts are my bone builders. During the process of growing, we are making more bone tissue. So osteoblasts, during the process of growth, so from birth all the way through adolescence, really until your growth plates close, your osteoblasts are always the most active. We're building new bone tissue. When you reach adulthood, so 21 to maybe age 40-ish, during that time, your osteoclast activity typically matches the rate of osteoblast activity, meaning the rate that I break down bone tissue is the same as the rate that I'm building bone tissue. See, in your body, we're constantly breaking down bone tissue and constantly building new bone tissue to make sure that your bones are as strong as possible. If we change the way that we walk, if we start to do different kinds of exercises repeatedly, those are the kind of things that would tell our body to rebuild our bone in a particular way. So in normal circumstances, in the average adult, the rate that you are breaking down your bone matches the rate that we're building new bone. Audrey asked if this is once the growth plate has closed or if it's later than that. Yeah, so this is typically going to begin right around when the growth plate closes. And it's typically going to last maybe into a person's 40s or thereabout, maybe a little bit later than that. But this is kind of early adulthood, if you will. The rate that we break down bone equals the rate that we form bone. And if we build it at the same rate that we break it down, our overall bone density, that's a word you're going to see a lot in the disorders assignment. Bone density, that's the amount of bone tissue that you have, or basically how much calcium is in the bone. If the rate that I break it down equals the rate that I form it, my bone density doesn't change. The amount of calcium in my bone is equal. That's good news for my bone tissue. We can get into issues as we age, and especially in individuals with osteoporosis, which is one of the disorders that you're going to study. The problem in osteoporosis is I resorb, or I break down my bone tissue faster than I build it. So in other words, I'm stealing the calcium that's inside my bone tissue, and I'm not putting it back into the bone tissue. Over time, we go from high bone density to much lower bone density. The lower bone density that's more prone to breaking, like we see here. So the issue with osteoporosis, which you're going to read more about, is the fact that your osteoclasts keep breaking down bone tissue, but those osteoblasts don't build it back up. If I resorb bone faster than I build it, that's a problem for me. I'm going to lose bone density. In addition to osteoporosis changing your bone density, the other thing that can change bone density is the endocrine system. The endocrine system. We talked about that only very briefly in week 1 in lab. How would you describe the function of the endocrine system? What's the function of the endocrine system? What does that one do? Yeah, my endocrine system, friendly reminder for us, anytime you hear endocrine, you should be thinking hormones. Hormones. So when I think about the endocrine system, and I'm thinking about my skeletal system, there are 2 hormones that primarily are involved in this process. In the process of calcium homeostasis. See, here's that homeostasis stuff back to haunt us, right? It comes up again. Remember that homeostasis means we generally keep things at about some normal state. So my set point, remember it's a range, right? My set point is 9 to 11 milligrams per 100 mils. This is how much calcium I want to have in my bloodstream. Now, please make a note for yourself, or please remember this. I will never, ever ask you to memorize this number. Please don't waste your mental energy on learning this number for me this semester. You don't need to know that for me. You might need to know it for another class later, but not for me. I will give you this number on the exam if we need it. My set in the body, 9 to 11 milligrams for 100 milliliters. If I don't have that much calcium in my blood, if I've moved away from my set point, that's going to activate what are called my parathyroid glands. So let me circle these guys. The parathyroid glands. The parathyroid glands are these little tiny glands that you see on the back side of the thyroid gland. So the thyroid gland, if you're looking at our lab models, you can see it on top of the trachea. It looks kind of like a butterfly. If we were to go to the back of the neck, when we look at the back side of the thyroid gland, you see these little things called parathyroid glands. Their job in life is to monitor how much calcium there is in the bloodstream. When the calcium level gets low, the parathyroid glands say, uh-oh, this is not what we're supposed to be at. So the parathyroid glands spit out parathyroid hormone. That's what PTH stands for, parathyroid hormone. That hormone goes into the bloodstream, and as it goes into the bloodstream, it tells osteoclasts, I don't have enough calcium. I need you to break down some bone to get me some calcium in the bloodstream. So parathyroid hormone tells the osteoclast to kick into gear. This is their green light, if you will. Green light hormone to the osteoclast, telling them, hey, speed up. We don't have enough calcium in the bloodstream, and the place that we have lots of calcium is in the bone tissue. Osteoclasts break down the bone tissue. That brings us back to homeostasis. That'll bring us back to our set point. Now, when we talk about calcium homeostasis, the action of my effectors, my osteoclasts, it's the opposite of my stimulus. My stimulus was calcium's low. My effectors make calcium higher. Calcium homeostasis. Is this an example of a positive or negative feedback loop? If my effectors do the opposite of my stimulus. Yeah, exactly. Calcium homeostasis is an example of a negative feedback loop. I'm doing the opposite of what I detected. If calcium gets low, I'm going to tell my osteoclasts to make calcium higher. It's possible for the opposite to happen as well. And that's what we see over here on my other side of this loop. And we'll fill in this other side together. Let's say that instead of your calcium levels getting too low, let's say we just drank a bunch of milk and ate a bunch of ice cream and took a calcium supplement, and our calcium levels are suddenly high. If your calcium levels become high, this is something that we're actually going to respond to using the thyroid gland. The thyroid gland. So this is that butterfly-shaped gland that the little parathyroid glands, they live inside of it, or they're attached to it. If calcium gets too high, it's not these little 4 dots that are going to respond. It's actually the big thyroid gland that's going to respond. So I've got too much calcium. My thyroid gland says, oh, this is not right. We have too much calcium. The thyroid gland is going to spit out a hormone called calcitonin. Calcitonin. Now, here's the way that I like to remember what calcitonin does. Calcitonin has this ending part in. When the thyroid gland spits out calcitonin, this is a message to tell the body to put calcium into the bone tissue. Calcitonin, our goal is for calcium to be in the bone tissue. Now here's where it gets tricky. When we spit out calcitonin, calcitonin is a message that also talks to osteoclasts. Calcitonin is another message that osteoclasts hear. Let's remind ourselves for a moment, what is the function of osteoclasts? What do osteoclasts do? Yeah, so osteoclasts are bone breakers. Osteoclasts break down bone. Here's a reminder for us. Break down bone, release calcium. Move that for us. Osteoclasts are bone breakers. When they break down bone, that leads to calcium being released. So if I've already got a bunch of calcium in my bloodstream, I want my osteoclasts to stop breaking down bone, to stop putting new calcium into the bloodstream. So when my thyroid gland spits out calcitonin, Calcitonin is a message that osteoclasts hear, kind of like a red light. Calcitonin tells the osteoclast to slow down. Stop breaking down that bone tissue. You break down bone tissue, it gives us more calcium. We don't need more calcium. Yeah, I like it, kind of like Kira said. Calcitonin is the message, dude, bro, chill, like slow down. We don't need any more calcium in the bloodstream. Here's the cool thing. If we tell the osteoclast to stop working, what it ends up looking like in your body is it actually looks like the osteoblasts are working harder. Because remember, when we talked about in adulthood, remember, did we say that normally osteoclasts or osteoblasts are working harder? Do you remember? When the growth plate closes, how does the rate of osteoclasts compare to osteoblasts? Yeah, exactly. We're talking usually, so normal conditions. This is when we said that osteoclasts, their activity is equal to osteoblasts normally. So here's what happens. Thyroid gland spits out calcitonin. Calcitonin tells those osteoclasts, dude, man, chill out, slow down. Suddenly, the osteoclasts aren't doing their job as much. So what ends up happening is my osteoclasts are not working as hard as my osteoblasts. So after calcitonin. When we spit out calcitonin, those osteoclasts slow down and the osteoblasts start working more quickly, or it looks like they are. In actuality, they're doing just the same as normal, but these guys are slowing down on the job. I always like to compare this because I'm sure we've all had this life experience. At least one time in your life, you have been at a job, or maybe it's with your siblings at home, where you look like you're the hardest working person in the world because somebody else is super lazy, right? So they hire that new person who knows nothing and who doesn't want to learn. They don't do their job, which makes it look like you are the best worker ever, right? No, let's be real. You actually are the best worker ever, right? But they make you look like you're even better. That's what happens here with calcitonin. It's not that the osteoblasts work any harder. It's just that the osteoclasts slow down. So we're no longer putting that calcium into the bloodstream. If we're not putting any new calcium into the bloodstream, then we're just pulling calcium out of the bloodstream and building new bone tissue, which ultimately will make the calcium level go down. This is a really important idea. I need to give you a moment to pause and collect your thoughts and tell me what you're thinking or what you would like some more clarification on. Let me give you some time here. Shoot me an honest emoji. What do we think about calcium homeostasis? where are we at right now? Okay, so we got a little bit of a mixed bag. Kira's gonna go drink a cup of milk. That's excellent. Yeah, so got some mind blown, got some tears. Here's what I would recommend with this. Remember how I told you all at the beginning of the semester that there are some things that it would be really good for you to explain out loud, either to yourself or to a classmate or to someone who's not even in the class. This is one of those things that we really need to make sure we understand. Because here's a Dr. Aulis promise. Wink, wink, nudge, nudge. This is what it looks like. Here's what the body does to get back to normal. You know what I'm going to ask you about on the exam? I'm going to ask you, what if the body makes too much calcitonin? Or what if the body doesn't make enough calcitonin? Same thing down here with parathyroid hormone. What if the body makes too much parathyroid hormone? Or what if the body doesn't make enough? I'm not going to take class time today to talk about that because I want you to really try to hash that out. So here, let me type up for you so you know what questions you're trying to think about this next few days. What if the body made too much calcitonin or parathyroid hormone? What if the body made too little calcitonin or parathyroid hormone? I want you to promise me that between now and Friday, you try to answer these questions. We can definitely talk about them on Friday if we'd like to, but I want you to try to think about it between now and then. What if I send this message too much? What's going to happen to the level of calcium in my blood and to the level of calcium in my bone? Or if I don't make enough of this message, what's going to happen to the level of calcium in my blood and the level of calcium in my bones? That actually reminds me, let me clarify something for you, and I'm going to attempt to draw, so bear with me. Here, I'm going to attempt to draw us. That's not a terrible bone, okay? So we've got a long bone there, and then we've got some blood next door. Here's what you need to be thinking about with calcium in the body. I have two places in the body where I find calcium. Place number one is inside your bones. Your bones are really awesome at storing calcium. And actually, we need calcium to be stored in the bones for them to be strong. But the other place in the body where we need to have calcium is in the bloodstream. Because when we start talking next unit about how muscles contract or how neurons send messages, they're going to need to be able to get the calcium that they need. So I need calcium in the bloodstream and I need calcium in the bone. When we talk about these hormones are going to have an impact on this cycle. Either they're going to take some of the calcium out of the bone and put it back into the bloodstream, or they're going to take some of the calcium out of the bloodstream and put it into the bone. So keep that in mind as you're thinking about calcium homeostasis. If the amount of calcium goes up in your blood, that means it went down in your bone tissue. Or if the amount of calcium goes up in your bone tissue, that means it went down in the blood. So there's always this, again, kind of like a circle of life thing going on. If one goes up, the other one had to go down to make that happen. So think about this circle of life. Think about our negative feedback loops like we see here. Consider how they normally work. Make sure we can explain as simply as possible what each of these hormones do. And then consider what would happen in your body if we had too much or too little of each of these. In the little bit of time that we have left, yeah, I'll comment. Somebody had mentioned this, that this is the idea of where bone disorders comes in. 100% accurate. While our bone disorders aren't necessarily issues with parathyroid hormone or calcitonin, they're going to be issues actually with other hormones potentially. This whole idea of needing to keep these two balances correct, the amount in the bones and the amount in the blood, 100%. That is what causes bone disorders. A couple of those disorders are issues with calcium. One of them is an issue with the collagen. If I don't make good collagen, that's a problem too. But if I don't have enough calcium because I've got some issue in this circuit here, if there's not enough calcium in my bone, that is problematic. So good segue or good tie-in to those bone disorders, absolutely. Here's something that I want you to consider as you are getting ready to do the bone disorders assignment. Notice that I've got this graph here that's showing me my bone mass or my bone density. It's the same thing. It's kind of a measure of how much calcium is in your bones. So from the time of birth up until about ages 20 to 30, so somewhere in the range of 20 to 30, everybody hits their peak bone mass. Now, for men, that peak bone mass is maintained maybe into the mid-40s, and then it starts to kind of slowly decline with age. So over time, it's just the way it works. Bone mass goes down. That's the same thing that we see in females as well, but notice that in females, there's a sharp decline in bone density following menopause. Now, I am not going to answer this question for you. I am going to make you figure out this one in your group me and figure it out on your own. Based on the fact that when a woman goes through menopause, she stops making estrogen, I want you to predict what effect estrogen has on our bone cells. So let me write your question here. What effect does estrogen have on bone cells? So there's two kinds of cells that we could talk about here. So I want you to predict what effect it has on osteoblasts and predict what effect it could have on osteoclasts. Here's my wink, wink, nudge, nudge for you. Menopause equals no estrogen. So when a woman goes through menopause, she stops making estrogen and she loses a lot of bone tissue. I want you to predict what effect estrogen has on these bone cells. So if you haven't already, take a screenshot, write down the question. I want you to consider this with your classmates. What might estrogen do to this calcium homeostasis? Let's talk about something that's not quite as scary as osteoporosis. Let's talk about something though that many people probably aren't excited about either though, which is braces. When you talk about orthodontia, which is what braces is, doing orthodontia, this is actually a great example of how we can use osteoblasts and osteoclasts to remodel your bone tissue. So when we start with the tooth, we can see it here. This tooth is apparently too far lateral. We need to pull it medial. So when a person gets braces, they put some metal anchors on the tooth, then they wire those two teeth together, and then they tighten that wiring to pull the teeth in a direction. So again, this tooth I'm pulling toward the middle. So here's what's happening. This tooth is being pulled this direction. So as I pull the tooth this direction, we have some pressure being put on this side of the tooth socket. That pressure activates the osteoclast cells that I see over here. Remind me in the chat, what was the job of osteoclasts? What do osteoclasts do? Yeah, exactly. This clast part's the breakers, right? So my tooth is getting pulled toward the middle, and the middle of this tooth socket is getting a whole lot of pressure. The osteoclasts feel that pressure and say, hey, we shouldn't have all this bone tissue here. We're getting squished over here. Let's break down some bone tissue over here. At the same time, on the lateral side of my tooth socket, we've got way less pressure than normal because this tooth is being pulled away from this side of the socket. So the osteoblasts say, wow, we've got room to grow and expand over here. So the osteoblasts start to build new bone tissue. So over time, what happens, so here's my little dotted line that shows us the original tooth socket. We started with an open space right here, but when the tooth scooted over, my osteoblasts filled it in. They built all this new bone tissue that I see right here, filling in this space. And over here, where we used to have all of this space filled in with bone tissue, my osteoclasts broke it down, or they did bone resorption. By breaking it down, we're actually able to physically shift this tooth from farther left to farther right. So the process of orthodontia is I break down bone tissue in the direction I'm trying to pull things, and I build new bone tissue in the direction where I was. So every semester, students ask me about retainers, what the goal of retainers is. The goal of retainers is to make sure that when my teeth have started to move over, so those osteoclasts have made space for it, retainers are going to make sure that my osteoblasts can keep up and build good bone tissue next to that tooth. So you do the really high force orthodontia and pull things. And then once we're done really pulling things, to make sure they don't move back the other direction, to make sure those osteoblasts keep the teeth in the right place, we'll use those retainers to hold them where they belong. So orthodontia, an example of osteoblasts and osteoclasts working together. Fanshan's asking an interesting question. If a menopausal woman would have to stay in braces longer? That's a very interesting question. I don't for sure know the answer to that. Yeah, that's a very interesting question that I will need to do a little researching on. As someone who did not get braces as a child and hopes to maybe one day get my teeth straightened, I hope that's not true. But yeah, so the question that I will try to do a little researching on, do you have to wear braces longer if you get your braces after menopause? That's a great question. I'll see what I can find out for you. One last thing to mention is the effect of gravity on the ability of your bones to be strong. So when we first sent people into space, when you're in space, there's no gravity to pull on you. We didn't fully think through the effects of gravity on the skeletal system. When the first astronauts came back from space, their skeletons looked like they had aged dramatically. I think there's exact numbers in the guided lesson, and I'm going to quote them wrong. So check that out to be sure. But I think it's something like your skeleton for every week or something ages like multiple months, like it would on Earth. It's a rapid aging because gravity pulls on your skeleton and makes sure those osteoblasts are working hard enough to make your skeleton strong. We can't remake gravity when you're in space, at least not yet. So the next best thing that we can do when we're in space is we can do exercise. So this astronaut here is hooked up, she's monitoring her heart rate, but she's also doing high intensity exercise, pulling on her bones, trying to make sure that there's still pressure for those osteoblasts to keep building bone tissue. There we go. So Kira quoted it for me. 1 month in space, 1 year on Earth. So aging the skeleton dramatically, especially if you're in space for a long time. So astronauts show us just how important it is to constantly have gravity pulling on your skeleton. By constantly pulling on your skeleton, gravity keeps those osteoblasts active, keeps them doing what they're supposed to be doing. At the very end of the lesson number 8 packet, you have these questions. I'm also missing because it ate it. How is the integumentary system related? We talked a lot today about how the endocrine system is related to the skeletal system. So we talked about parathyroid hormone and calcitonin. We talked a little bit just now about how the muscular system is related. This is why astronauts are exercising in space, because the muscular system has an effect on the skeletal system. When we think about the digestive system, consider that the digestive system is going to be your source of dietary calcium. So that's our relationship here. The relationship of the integumentary system is something that you'll actually see more once you've completed those skeletal system disorders assignment. Yeah, so I've got a couple of people in the chat that are helping us out here. The integumentary system, your skin, is what we use to actually make something called vitamin D. Vitamin D. This is a vitamin that helps your body to absorb calcium. So your skin is the way that we make vitamin D. We sometimes call it the sunshine vitamin. You need vitamin D to be able to absorb the calcium in your diet. So 4 different systems that all relate to the system we're working on. This is an idea, I'm pretty sure it's listed in your notes. Big picture idea in anatomy and physiology. It's called the interrelatedness of organ systems. The interrelatedness of organ systems, meaning nobody functions by themselves. The skeletal system can't do its job without the endocrine system and without the integumentary system and the digestive system. So the closing idea for lesson number 8 is this interrelatedness of those systems working together. That is all I've got for today. I saw a question in the chat about visible body. Yes, you have some visible body assignments that are due this Friday. So tomorrow during class, we're covering lab stuff. You're going to have visible body assignments related to the muscles of the thorax and abdomen and the bone markings of the thorax and abdomen. So those are due this Friday before you head out on spring break. And then we won't have assignments again until the Friday after spring break. So we'll look a little bit more at that tomorrow. That's visible body for this Friday. The other thing, again, due this Friday is lesson number 7 for lecture. So make sure we get lesson number 7 done ASAP. Ideally, lesson number 8 as well. All right, well, if there's no other last minute questions, I am going to shut off the recording. I will stick around for any questions that you have. Otherwise, I hope to see you all tomorrow to cover this week's lab stuff.